Now, temperature is all about the average kinetic energy. And we can summarize that by saying energy, subscript K, means kinetic, so kinetic energy. And that it's going to be related to how fast something is moving and how heavy it is, speed and mass. Now let's consider the relationship between those a little bit and see what that's going to tell us about different gases. Now, this is our relationship for kinetic energy. You can see here that it says that average kinetic energy equals half of the mass times the square of the average velocities. And that's what U here is. We'd probably think of that as being V, but let's face it, there's enough V's already in our lives, so they're using U for speed. Now, another way that you'll commonly see this written is something called root mean square velocity, and that's not something I'm going to get into much here, but if you're talking about root mean square velocity, it equals the square root of, I'm just completing the square root sign there, 3 times r times t divided by the molar mass. And notice that here, molar mass actually needs to be given in kilograms per mole, which is a little bit weird for us, but not a hard thing to do. We just need to divide by 1,000, and that gets from our molar mass into kilograms per mole. I'll mention why that is at the end of this video. Now, suppose we have two gases, and they're at the same temperature. Makes sense, right? Well, that means that the average kinetic energy is going to be the same. However, the heavier one is going to move slower. The lighter one's going to move faster. So that these expressions still end up being equal, since they have to have the same average energy. So mass can be different, and then velocity can be different as well. Or if we're looking at root mean square velocity, velocity will drop as we have heavier molecules and will be high for light molecules. Now, this is what actually happens if we plug through the calculations. You can see O2 gas, which has a molar mass of 32. Oxygen is 16 times 2. Nitrogen is 28. Water is 18. Helium and hydrogen gas will have 2 AMUs as its molar mass. Now, when you plug all that into these calculations up here, you'll find that we're going to plot the relative number of molecules with a certain speed. Oxygen, at a certain temperature, is moving far, far slower than nitrogen or water, dramatically less than helium, and insanely slower than hydrogen gas. Remember, these are all at the same temperature. Now, if we have a thought experiment for a moment, suppose that we're talking about a vinyl balloon or a latex balloon or something like that, and we know that there are going to be microscopic holes in it. Nothing's perfect, right? So if I have it filled with oxygen, nitrogen, and maybe some carbon dioxide and water from my breath, and I blow up this balloon, and I fill a different balloon with hydrogen, and we know there's a small hole, well, how often are they going to find that hole? These, at the same temperature, are going to be moving really slow, right? They're occasionally going to get to the wall. They're occasionally even going to find that hole, and once in a great while, one of these molecules will sneak out of that hole. Hydrogen, however, is moving fast. It's going to find every hole that's in that balloon really fast, really often. And also point out, it's also going to be really small, so it has an easier time finding just the right angle to hit that hole at, so it doesn't just bounce off anyway. These molecules are going to be bigger, or atom in this case, are going to be bigger and have an easier time ricocheting off. Hydrogen is going to get through it pretty easily. This is why if you've had a hydrogen balloon and a breath-filled balloon from a birthday party blown up at the same time, your hydrogen balloon was a shriveled up raisin a few hours later, just about, right? The next day, right? And your breath-filled balloon was probably still fine a week or two later. It's because these are moving so much slower, because they're so much heavier, and because the kinetic energy has to stay the same between them. Now, I'll point this one out too. Average kinetic energy equals 3 divided by 2 times R divided by the Avogadro's number times temperature. This is another way that you can determine and convert between kinetic energy, number of moles, and temperature. But I really want to point something out here. If we're thinking of R as being the version of R that we usually don't use in the ideal gas law, the one that's actually going to have units of joules over, let's see, trying to remember what goes on the bottom there. So it'd be moles Kelvin. There we are, moles Kelvin, joules per mole Kelvin. Well, if we were to expand that out and we think about this unit, in fact, right there are, you can see that joules is going to be our energy unit in this case. Now, if you remember back, when we defined joules, we said that inside of joules, we've actually got the units kilograms, meters squared, divided by seconds squared. Well, it turns out that if you go through all of the work of doing these calculations, what you're going to end up finding out is that the kilogram that you have here never does cross-cancel, and neither does just the prefix. This is actually why these molar masses have to be in kilograms per mole in order to cross-cancel with what we have down here, hiding in this version of the ideal gas constant. Now, that said, it's not a real big deal for us. It's easy enough to do that conversion quickly. But that's the reason for it. And I'm not going to show the derivation, but if you search online, you can actually find a derivation that shows exactly how everything cross-cancels very nicely.